Recording. So again, thank you for joining us, and I hope that we will present to you all of that you will follow us. For those who have been following us, and for those who are newly here or following relatively fresh the project, again I welcome you all, and I'm going to give you a short introduction about our project. So what we are doing here is we are focusing on hydrogen refueling stations. So with the increasing demand for fuel cell vehicles, just cars, but also heavy duty vehicles, buses, trucks, and also trains, there is demand for upscaling of the number of refueling stations, which might be co-located alongside conventional fuels in commercial and residential areas. So the issues that we have with this is that in some countries, specific regulations for HRS don't exist. Some countries they do exist, but they are not specified. They are combined with some other fuels. Of course, co-location of hydrogen with conventional fuels is not seen in most safety regulations, and this is what we wanted to explore with this project. So what we did was we did some analysis, both desktop research, and my colleagues did also experimental research. And with this, we wanted to provide some feedback and some information on what has been done until now and what needs to be done, provide some recommendations regarding the outputs that what are the next steps in co-locating hydrogen refueling station next to conventional fuels. The goal, as I mentioned, is to define commonly applicable, effective, and evidence-based guidelines to facilitate the construction of hydrogen refueling stations and multi-fuel refueling stations. Actually, in these multi-fuel locations which would be suitable to have both. So what we did was to identify relevant gaps in the current legal and administrative framework, which I will present afterwards. We gathered some experimental data from engineering research and leaks. We also engaged with relevant stakeholders, actually with a lot of stakeholders, some of which are here with us today. We actually had over 100 applications for these registrations for this event. So a lot of them are interested. And of course, we want to successfully disseminate the project's results, so they are available to everybody who is working in the hydrogen refueling and refueling stations sector. This is our consortium. We have partners from all over Europe, as you can see. As I mentioned, Hydrogen Europe is the coordinator of the project, as well as the work package leader of work package 1 and work package 4, where we engage with stakeholders, or where we defined the legal analysis of the situation in here. So you can see here the work package structure. I'm not going to go into details because it's quite a lot. But what the focus is, we have 6 work packages. Work package 6, project management, and work package 5, dissemination, communication, exploitation, are usually typical for these types of projects. What we started with is work package 1, as I mentioned, detailed investigation of current status, which is feeding into work package 3, where we wanted to generate best practice guidance, which is actually the focus of this event. Within work package 2, my colleagues will show you and present you the practical research which was done with experimental data they obtained to address gaps in current understanding of hydrogen refueling station in general, not necessarily related to multi-fuel statuses and co-locations. And of course, we have work package 4, which is engagement, where we wanted to engage with the stakeholders, so with the refueling station operators, with the public authorities, to assist them in deploying these regulatory information, this experimental data, where they see fit, and how we can try to help them as much as we can. The project started in 2021, which was quite some time ago. We ended up in September last year. unfortunately, we had a couple of bottlenecks in between because we had the COVID. We had some additional administrative issues in between, but we are here at the end and we're trying to present the final outputs, which will be uploaded for everybody, to everybody's availability. With that in mind, you can see our website here. You feel free to check it. All of the outputs of the deliverables, which are publicly available, are uploaded on the website. It has a summary of the project, the public deliverables, as I mentioned, slides and recordings from launch event and workshops in between, as well as it will hold the recording of this event, news from the project that we had, and of course, the communication, dissemination, exploitation plan that we had from the beginning of the project and at the end of the project. It also has a contact email where you can get in touch with us with the questions that I mentioned, but in the end, I will show you also this email with an additional email where you can send your questions, where we can try to respond to you as detailed as possible, so you have all the information that interests you. So with that in mind, I would move on to the next step, which is this deliverable that I mentioned, the permitting requirements in Europe. I'll go shortly through it because you can find the final deliverable online on the web page that I mentioned, where you have all the details of the information that we gathered, that we collected. So we have two deliverables related to this task. One is something that we did in the beginning of the project, where we gathered information from 14 countries. The other one is at the end of the project, where we refreshed this information to check whether something has changed or everything stayed the same. So the focus of this, as I mentioned in the beginning, was to define commonly applicable, effective, and evidence-based guidelines. And to do so, we needed to identify the gaps in current legal and administrative framework. Not just the gaps, but also what is the current status of this legal administrative framework. So what we did was to examine 14 countries through 14 organizations that we got in touch with. So the national expert that we were in touch with, and we asked them to provide us assistance in order to do the comparative assessment and gap analysis. So we asked them to check the existing permitting requirements for HRS, the risk assessment regulations and methodologies, safety or separation distances, and intervals and content of equipment maintenance. So I marked here France and Netherlands. My colleague vastly provided information on these two countries. We had most details on these two countries in the last iteration process. But I will show you the results of everything else as well. So what we did, what we had feedback is that we had 4 countries with specific HRS regulation and refueling stations which were deployed. We had 7 countries without specific regulation, but with refueling stations deployed, meaning that they had refueling stations implemented, but their regulation was actually based on some other regulation that was available for refueling options. We had, of course, 3 countries without any refueling stations deployed, which also didn't have any regulation implemented for this purpose. The process was quite long, so we had 5 to 6 months on average for each partner, each country to gather, each organization to gather information on the country level, the national level. And what we got information, so feedback, that there are regulated time limits for granting permits after submission of the application, but even in those cases, they can be surpassed. So this is a long time, both to gather the information, but also to try to push something, actually to try to implement refueling stations. And the general takeaways that we got in the end is that the process is not standardized in most countries. A lot of authorities need to be involved from the very beginning. Most rules applied refer to CNG rules or hydrogen used in industrial context. As I mentioned, we had countries which had hydrogen fueling stations deployed, but not specific hydrogen related rules. And in some cases, we had overly cautious measures put in place just to be safe, which are not necessarily technically feasible or needed, but just to be on the safe side. And of course, the safety distances that are determined are very different among countries.
Excuse me, Dinko. Apologies for the interruption. There are quite a few people in the lobby waiting to be let onto the webinar.
Okay, thank you, Liz.
Okay.
Please feel free to let me know. As I mentioned, this is a bit of an issue since I'm doing this myself and challenging to check everything, but thank you a lot.
Okay.
So just to move on, I'll try to keep this part short. As I mentioned, everything will be online, so you will be informed. So the recording will be available online, and you can check if you joined later. You can check what has happened before, what we discussed before, and what we will discuss afterwards. So what we had also, this is just a summary of a couple of countries, just so that we can show you the differences between countries that we gathered information from. So we got France, Germany, UK, and Finland here. You can see what are the differences regarding the distribution of hydrogen storage, size of storage, how it relates to distribution, and how it is specifically determining some points where planning is considered, where safety is considered, where transport is considered, and other different but also important aspects. Some countries do have it, some countries don't have it, and this is quite interesting to see because from experience, what we gathered in communication with the relevant public authorities, for example, in countries that do not have at the moment the regulatory framework for hydrogen refueling stations, they can check in countries that do have it, how have they deployed refueling stations, and maybe try to, we didn't always recommend copy paste, of course, of the regulation, but to see what are the experiences and what are the suggestions of those countries, how they implemented it, so they can apply it to their local levels. Okay, so as I mentioned in the beginning, France and Netherlands, we're going to use this as an example. You have regarding authorities in charge. There are different authorities that are in charge of deployment of hydrogen refueling stations and granting approvals to put them online. For example, in France, this is the mayor of the city, which requires, of course, support from other entities, regional authorities for the environment and safety. On the contrast, in Netherlands, this is the municipality who issues the permit but gets advice from other entities as well. In regards to existing guidelines or regulation that needs to be followed, in Netherlands, there is an online guideline with specific information, while in France, there is a specific declaration which is focusing on hydrogen refueling station itself. In regards to risk assessment methodologies, we have in Netherlands the Seveso directive, which refers to the ISO standards, which determines the use of quantitative risk assessment. While in France, risk analysis is only mandatory for installations subject to the authorization regimes, meaning that more than 1 ton of hydrogen storage, if it's applicable, then the risk analysis is needed. Below that, it's not. As I mentioned, I'm not going to go into details regarding these specifics because you can find them in details for each specific country in the deliverable that is online, which is related to the permitting requirements. Just to give an example for safety distances, so you can see here, this is in between hydrogen storage and pipeline is determined in Netherlands, while in France there is no prescribed rule. On the other hand, in distance between hydrogen equipment and other fuels is determined in France, while not in Netherlands. The main takeaways that we got is that, which can be concluded from this small example, that some countries do have specific hydrogen refueling station specific legislation in place, normally commanding the development of quantitative risk assessment with available risk assessment criteria, while other countries do not have these guidelines, which from one hand allows more flexibility to the operators, but requires more effort in finding the right data for achieving a successful permit and also the environmental permits specifically. But on the other hand, this might be quite challenging because it doesn't give them the guidelines which they can follow step by step in order to implement this information and deploy the hydrogen refueling station itself. What I mentioned also in the one point, you can find these detailed documents online. So deliverable 1.2 and deliverable 1.4, the permitting requirements and risk assessment methodologies for HRS in the EU. So we had the first version in the beginning that I mentioned, which was the status in 2021. Then we had the final analysis and comparison of the results, what has happened in the meantime, which was sometime in 2024. And both documents are publicly available online in detail for the 14 countries, which you can check on the website. And with that, I would finish my part. I move on to the experimental part of this event, where we present the final deliverable D3.7, which my colleagues will present. And starting with Julien, I would give her the floor now. She will present you the structure in terms of references of the document, how it was created, and other colleagues will move on with the specifics of the document. What I want to mention before giving the floor to Julien is that we are not going to present the entire document today. The document is quite long. I would suggest, if you're interested in details, to check it online. It will be available after the event, alongside with the recording of this event. If you have any questions, I mentioned in the beginning, but for those who joined us later, you can ask them in the chat. Of course, if my colleagues have the opportunity to answer you, they will, but we suggest that you can send us your questions, specific questions via email. We will gather them and provide a Q&A for all the questions and send to all the participants. With that, I'm giving the floor to Julien and to her presentation. Julien, the floor is yours.
Thank you, Dinko. Can everyone hear me okay? Yep.
Yes.
Okay, yep. Good afternoon, everyone. I'm Julien Saw from the Health and Safety Executives Science Division. It's lovely to see so many of you taking an interest in a project that we have worked hard on for the last 4 years. So for the next 5 minutes or so, I will be giving you a quick overview of the final deliverable of the project that all MultHyFuel consortium partners have collectively produced. So the final document is entitled Developing Good Practice Guidelines in Project MultHyFuel, and it's made up of deliverables 3.7 and 3.8. It is the output of task 3.7 of the project that brings together all the work within the MultHyFuel project. So in terms of its structure, section 1 of the document, so Dinko, could you move to the next slide, please? So section 1 of the document provides some background information on the MultHyFuel project. Section 2 then lays out the terms of reference of the document and the caveats behind it. Section 3 makes reference to the existing permitting requirements for hydrogen refueling stations within Europe, as per the talk that Tinko's just given. Subsequently, Section 4 summarizes the risk assessment methodology adopted by the consortium that enabled the project to develop a view on the risk picture and some of the factors that feed into this. So this includes the findings of the project experimental programs, as well as the potential consequence modeling approaches and techniques, and where there might be gaps in knowledge. So this section of the document aims to provide the reader with an idea of a possible approach to risk assessment and separation distances that have been estimated using consequence models and how they compare with our experimental results. So following on from this, Section 5 looks at some example technical recommendations on risk management measures that could be adopted in a multi-fuel hydrogen filling station in terms of the dispenser, the forecourt layout, and its operation and maintenance. The document then culminates in Section 6, which gives a summary of the technical recommendations, including some suggestions for further research to inform the potential development and/or update of codes and standards. Next slide, please, Tinko. Thank you. And now for the terms of reference of the document, specifically the important caveats behind it. So the development of the good practice guidelines has been born out of the MultHyFuel project and was developed based on the research on a finite and limited scope within the available resource, funding, and project duration. So there is bound to be elements which have not been considered, or indeed some of which will need to be developed further in future research work. So this document will need to be used with care, bearing in mind the boundaries, context, and limitations of the research. Where reference is made to EU directives, this should be read as the relevant national legislation which transposes the directive in the respective country within which the multi-fuel hydrogen refueling station operates. So the research and therefore the good practice guidelines within this document does not take into account each country's regulatory consents and land use planning implications, i.e. the location and siting considerations of the refueling station, and how potential major accident hazard scenarios from, say, the hydrogen bulk storage might impact populations in surrounding residential or industrial and commercial areas. So all of these will need to be taken into account in the risk assessment, subject to the regulatory control in the country within which the operator's multi-fuel station is located. It is also very important to highlight that the focus of the project's detailed research phase has been on the study of the risks arising from the hydrogen dispenser, but not on the bulk storage. For example, hydrogen storage, on-site production, and processing. These were actually considered during the early or preliminary risk assessment phase, including the hazard, but they are not detailed in the current deliverable. So these will need to be considered in the siting and design of the multi-fuel refueling station, and will include risks from all equipment, such as those from the process, the compressors, as well as temporary mobile storage like trailers, etc., parked for unloading at the refueling station and pipeline transit, plus conventional fuels grouped in the same area and the potential domino effects that could arise from these. So subject to the relevant country's regulatory and permissioning control, associated risks will also need to be considered and managed. For example, hydrogen refueling stations are likely to be in the scope of the Seveso directive, so conformance to its requirements would be required in Europe unless the inventory is managed to be below the lower tier thresholds at all times. Next slide, please, Tinko. Thank you. So we would like to stress that the experimental program within the project did not study liquid hydrogen releases. Because of the project scope, the findings of the research reported in the deliverable may only be specific to the assumptions made within the risk assessment, consequence modeling, and conditions of the experiments conducted. For example, in our large-scale experiments using the mock-up dispenser system, the release of hydrogen was not sustained at constant flow rate. There was a measured decay with time as a buffer tank was not used, whereas consequence models typically assume constant release rates. In addition, weather conditions may have a significant influence on the dispersion results. One other thing that is also worth pointing out before you read the report. So whilst likelihood and potential severity determine the level of risk, the techniques to determine the severity, i.e. the methods to estimate populations exposed to the harm, was not part of the work. Instead, the focus has been on the consequence assessment techniques that form part of the risk assessment process. So what I'm saying will make sense when you come to read the deliverable. The technical recommendations born out of the results of this project would be applicable to similar hydrogen refueling station configurations and dedicated equipment as those studied within the project, i.e. the 3 configurations covered and described at the start of section 3 of the document, and the assumptions behind this. So the application to a larger scope will therefore require dedicated risk assessments and additional validation. It is also important to highlight that the research has been conducted at a high level, hence the findings and recommendations made in this document are at a snapshot in time. However, we still believe that all the work that we have carried out in the last 4 years and the resultant research findings have not only helped us identify some key technical recommendations, but as with all good research projects, has also helped identify remaining knowledge gaps, which themselves would need further research in order to address and feed into the development and or improvement of various regulations, codes, and standards. More about this later. And that's all I have to say really on the structure and of the report and its terms of reference, hopefully setting out its scope and context. So I will now hand the floor back to Dinko.
Yes, thank you, Julian. So now heard what we have in the document. So as you heard, we have a lot of information with a lot of things that are quite specific, which we needed to focus on and which we wanted to specify. So which was quite challenging because when considering hydrogen filling station, you need to consider a lot of things. My colleagues did quite a good job at it, but we still have some things that we didn't have the chance to do within the project activities, and hopefully we will have the chance to do so in the future. But to move on with our research and to show you what we did, I'm going to give the floor to Sylvain regarding the risk assessment approach which we used. So you can see in which direction we started, so how we started in terms of the risk assessment. So then with that, I'll give the floor to you.
Hi, everybody. Thanks for your participations. Do you hear me well? It's okay?
Yes, we can hear you.
Okay, thanks a lot. So now I will present our two parts. So the risk assessment methodology, because the goals what you see at the end to realize guideline, but to realize this guideline, we had to know the risk on different configurations of refueling stations. And after I will show you how we estimate the likelihood. So next slide, please. So the objective to realize the risk assessments, it's, as I said, to know well what can happen in the hydrogen refueling stations to develop after the best practice guidelines. So what we make, it determines also the risk assessments can determine the recommendations for the safe implementations of hydrogen dispenser in the multi-fuel stations. And finally, the goal to realize this risk assessment is to confirm risk assessments and to give the priority for the experimentations to determine after the severity, the likelihood failure on dispenser accessories. So to realize these risk assessments, first on what is will we study. So for that, we make a benchmark on existing technology and equipment relating to the fueling stations, and we want to study 3 different configurations that were established in this case for the MultHyFuel projects. So this configurations is, so the 3 considerations, it's what the MultHyFuel stations can be now, but also what this hydrogen refueling station can be in the future. So the first configurations, the named ready to deploy multi-stations, it's a configuration based on existing and implementing technology. Hydrogen is supplied by a trailer or by bottles. So it's supplied by gas hydrogen. The second configuration is on-site hydrogen productions, and the configuration ban on a hydrogen production with an electrolyzer to meet the requirements of the fueling of hydrogen. The third configurations, it's something that we think can be in the future. It's to have a high capacity and high filling multi-fuel stations. And the configurations is based on future technology that may be developed, and it's based on liquid hydrogen. You can see just at the end the 3. Yeah, we are now see the 3 hydrogen configurations. So here it's the configuration 1. For each configuration, I will introduce on the left part, you will have a process, and on the right part, you have a layout. So here you see for the configuration 1, the trailer, the bottles to furnish, to supply the hydrogens. We have a compressor because, as you see, the pressure in the trailer is between an orbital, it's between 200 to 600 bar, and we would like to reach 1000 bars. So that's why there is a high pressure compressor, and after you have 2 storage, high pressure storage, and after you have a cooling system to be at the right temperature to fuel the car, and you have a dispenser. So here it's the process. Now if we are looking for on the right the layout, you see that there is one technical zone where you have find the storage, the difference, so the storage by trailer, the high pressure storage, the compressed feed, the chiller, and the control technical room. And on the right side on this layout, you have the dispenser with, you see there is different color. It depends the fuel that are dispensed. So here in blue, it's hydrogen. In orange, it's conventional fuel, still gasoline. In green, natural gas. In purple, electric. And you see that there is some dispensers that are dedicated to some fuels and some gas-free fuels. So I will show the next configuration. So here it was the first one configuration. The second one, you see that it's the configuration with the on-site hydrogen productions. Here you see that you have on the left part the electrolyzer, that after the storage, different storage buffer, low pressure, medium pressure, high pressure, with different compressor to increase the pressure, the cooling system, exchanger, and the dispenser. On the right side layout with, you see in the middle, the process and storage area, the technical area with, it's in this part that you have a production with a PEM electrolyzer and also the different compressor, storage systems, chiller. And after on each part, so on the left part, you have a dispenser for trucks, and on the right part, the dispenser for the light vehicles. And then you are fueling a dispenser dedicated to some fuels and it's hydrogens, it's liquid hydrogen. You have after a cryogenic pump to increase the pressure, hydrogens, vapor to transfer hydrogen, gas hydrogens, for hydrogen, the cooling system, and the dispenser. And here you see on the right side the layout with the different technical place for technical area. And here we think it's a high capacity and we fill only trucks. Next slide, please. So we determined, as we see before, the different configuration. After, we would like to see to make a state of art on the risk assessment methodology. So to realize this analysis, we are looking for scientific articles, but also we use lesson learned from partners. We see that when we read these articles about the risk assessment of hydrogen refueling station, risk assessments was realized with hazard methods or with preliminary risk assessment method. For the database, to estimate the likelihood, the more used database was the Popper Book or IRAM. For modeling software, they use the FAST system and IRAM developed by Sanjay in the US. For the critical equipment, what is critical, it's more the dispenser, because we are close to people, and the storage due to the high volume of hydrogens. The dangerous phenomena, there is explosions, unconfined vapor cloud explosions, flash fire, jet fire, or burst on hydrogen in case of overpressure. But here we are fuel systems. So for other fuel, we see that we have other also dangerous phenomena like pool fire for LPG, diesel or petrol, or boiling liquid expanding vapor explosion for LNG LPG. The first safety measure that we was recorded in this analysis, we see that friction to prevent shock inside the hydrogen refueling stations, safety valve to release overpressure to a vent, or gas detection combined to an emergency stop and isolation device. Next slide, please. Thanks. So now we make the risk assessments. To realize these risk assessments, so there is common cause that you can see in the blue circles that we analyze in the three configurations. So for example, embrittlement of hydrogens, we can have loss of containment, vibration, shock, backflow. But we also analyze some specific cause in the different configurations. So for configuration 1, for example, the trailer movement, or for the electrolyzer, the membrane installation defect. Next slide, please. Yeah. So now if we want to rank the different scenario, we use during the risk assessment different scale. So here you see on the left side the risk matrix for severity. So it was quality scale, just to see, let's go from 1 to 4, 1 minor accidents to 4 catastrophic accidents that where you can have more than one facility. And after you have likelihood system, and above, after we have the criticity, we have both the likelihood and the severity. What we have in red, it's because of as soon as we have one fatality, we consider that it's not we cannot open the hydrogen refueling station. So here at the end of this analysis, we have 258 dangerous phenomena. As you see in the different configurations of this, we have mainly for dangerous phenomena for the three configurations. It's fire, jet flyer, flash fire. We can have also explosions, dangerous phenomena like VCE, UVCE. We can have also asphyxia or fireball or wiping of hose. So it's common for the three configurations. We have also some dangerous phenomena that are specific to liquid hydrogen or others specific for the electrolyzer, like fire due to oxygen enrichment. Next slide, please. Yeah. Here it's for the dispenser, the major scenarios. We can have release with reaching flammable, with not reaching flammable and limits, and without or with immediate emissions. So we can have flame, or we can have a small explosion, or we can have also an internal release reaching the flammable limits, followed by ignition, and we will have a vapor cloud explosion. For hose and nose, we can have release with immediate ignition, so we have torch fire, or we can have delayed ignition and confined vapor cloud explosions. And for the hose, we can have also the release with whipping of a hose. Next slide, please. So here we have a major scenario. Now we will have to have in detailed risk assessments and to estimate the distance for each dangerous phenomena. So here it's the different effects that we the different results that we used to assess this different intensity of different scenarios. The scenario were modelized by partner software or also by commercial software such as FAST. So you see there is here the threshold for thermal effects, so for overpressure effects, so for example explosion, and special also for the whipping of a hose. Next slide, please. So here you can see when we make the intensity of each dangerous phenomena, so we have the lethal effect in purple, the major lethal effect, in red the lethal effect, and in orange the irreversible effect. And here it's the effect, for example, for dispenser. And we with this configurations, we estimate the impact on people on the vehicle, and also that we also estimate people that can be around, so the impact around the hydrogen refueling stations. Next slide, please. And yeah, here with VAST, we determine the severity levels, so to moderate for the lower to the disastrous for the worst, and we count the number of persons impact that the freeze all of significant lethal effect to the irreversible effect. And we also, for each dangerous phenomena, we use the scale at the bottom to identify the likelihood of each dangerous phenomena. Donc it's frequency per year, as you can see. I will detail just after how we make the likelihood. So for each dangerous phenomena, each scenarios, we classify in this rank. As you see, there is the likelihood A to E. It's more probable, like E, it's less probable, and disastrous to moderate, so for the severity. In red, it's what represent in red. It's identify risk reductions must be implemented. We cannot keep a scenario in this part. In orange, it's an intermediate risk zones, and we must implement some measure to be as low as reasonable, practical. We have to establish or to establish good practice if it's possible. So that's the we use. Next slide, please. So for the result of these risk assessments, it's that what we see, it's that the risk matrix we identified, so the number of scenarios that are not acceptable, so in the case red or orange, and we calculate the number of the scenario for each equipment. So what we see like that, it's identify the critical equipment. So it's the dispenser in the fourth, and in the barcode, it's storage, compressions, and equipment dedicated for liquids. About the dangerous phenomena, we can have, as you see, explosion. We see here unconfined vapor explosions, and also thermal effect, flash fire, jet fire, and in some cases, burst or the whipping of hose. Next slide. So here it's an example of different recommendations that we have. We have the recommendation of design, for example, design of roof, about the detection, hydrogen, flame, and gas detections have to be implemented in hydrogen filling station associated to emergency protocol. We have to choose material compatible with hydrogens. We have also importance to pay attention to the control of hydrogen fueling stations, and to monitor key parameters such as temperature, pressure on a different location on the hydrogen fueling stations. Next slide, please. So now I will focus on the likelihood. So the estimation of likelihood is a key component of risk assessments. There are a number of different approaches that can have and can be included, but here you see the three main approach: the frequency statistic, so it's derived from past incidents, commonly held in generic failure database, what we see just after, the Bayesian statistic, which combine both objective and subjective data based on expert judgment or lesson learned from past incidents, and the reliability of structure approach, which combines with physical characteristic and probability of human error independent of past incidents. In MultHyFuel project, we use two different methods: the frequency statistic for the first one, and the third one that I will just show you just after. Okay, next slide, please. Next slide. Thanks a lot. So here it's the first method. So it's a likelihood for generic failure database. So here in the tables, you can see here the calculations of the estimation of likelihood for two scenarios: the loss of hydrogens with the medium leak, and also for the full bore rupture for the different configurations, different pressure, different time to fill. And we make the comparison of three different databases. So BAVI, Sanja with a US database, and North Gas Profam, it's a Norwegian database. As you see here, there is a lot of difference between the different databases we have for one scenarios, we can be A to E, so we can have the large range only for one scenario. That's why we would like to develop another way to see this database. Next slides, please. So as you can see, for the generic failure database, the strand is very simple to implement. It's very generalizable. We consider failure mode specific to mechanical components. The weaknesses is the estimation of the likelihood does not consider the initial events because we estimate the likelihood at the central fear events. We do not valorize the barrier, or we don't consider also always the initial likelihood. So the model may not be also some 100% representative of new technology because it's based on technology that are in the industry. So next slide, please. So that's why we try to have another approach. It's the reliability of structure approach. Here we like to have an analysis based on the component of operations and to see what can happen. So here, for example, we can have mounting mishap, fatigue, misuse, wear, corrosion, and tightening. And for each different fact, we estimate the probability. Next slide, I will show you in the tables. Here you see the results. So you have the different component of the left side, the different solicitations, so fatigue, corrosions. And here on the right side, you have the failure of a component. You see, for example, that hose or nozzles are here in the red and are a high probability to have failure. Next slide, please. So this restraints of this method is taken account the failure mode specific to each mechanical components. We have a possibility to carry out sensitive analysis and optimization of certain parameters. We have a quantification of specific degradation mode for each components. We give an accurate picture of the impact of each cause and mode of degradation on overall equipment failure. But the weakness, it requires a good level of knowledge of mechanical and probabilistic model. There can be significant uncertainty in the numerous input data and also on mathematical models. The models may be difficult to generalize and apply to other configurations. And the determinist approach and the results correspond to a lifetime and does not allow you to benefit from the advantage of a probabilistic approach. Next slide, please. So for the conclusions, so we develop there is a new approach that is developed. So the reality of reliability of structure. We develop a detailed analysis of degradation mode depending on the component present in the system. This approach is new. It can be developed in the new technology system. But this is also the approach could consider more representative estimation of likelihood for hydrogen refueling station accident scenario. But however, this approach Excuse me.
I do hope that you can hear Slovene. Slovene, apologies, there might be some technical issues maybe on my side. I see that my connection is not very stable. So I do hope that you can hear us. So then, are you here?
Yeah.
Yeah. Okay. So thanks a lot for these inputs. We're going to move to the next part, which is experimental findings that we got. So we heard about the methodological approach, and now we're going to hear about the findings. We have a recording of our colleague Louise, which we will play, where you can see which were the experiments that were conducted during the project activities. So I'm going to find this, and please let me know. I'm going to start the video. If you don't hear it, please do let me know. But you should be able to hear the recording.
So I'm Louise O'Sullivan from HC, so that's the Health and Safety Executive in the UK. I work at the Science and Research Centre at Buxton, and today I'm talking about fire and explosion hazards on a forecourt. So today I'd like to state as a bit of a disclaimer that this presentation doesn't form policy for HC and isn't current HC policy guidance, which is my bit of housekeeping to do, and also a bit of a noise alert. So third video in contains noise. So if you'd like to adjust your own volume at that point, please feel free to do so. If you're in a shared office, it can be a bit disconcerting for others when they hear that. Thank you. So we've spoken before around the purpose of MultHyFuel as a project, and it was created as it was seen there was a lack of guidelines and instructions for local authorities across Europe and the UK for the deployment of multi-fuel forecourts. And it's creating a barrier to successful rollout for hydrogen refueling. So the project aims to produce good practice guidelines which could be adopted both by industry and local authorities to enable the rollout of multi-fuel forecourts. Next slide, please, Joanna. Thank you. And as Christophe explained to you before, we're working as part of a full consortia on Work Package 2, working with other Work Package 2 leaders, Ineris, Kiwa, ITM Power and Shell, amongst others. And our work has been undertaken to determine leakage frequencies, flow rates and the extent of hazardous zones for faults on HRS plant, as shown previously. But also we've conducted experiments to demonstrate the effect of hazardous occurrences on hydrogen dispensers and how this affects different dispenser types on a forecourt and a multi-fuel forecourt scenario. So how this affects both traditional petrocarbon fuels and also looking to the future. In the final part of Work Package 2, we will test the performance and reliability of key safety barriers, as identified by Christophe earlier. And we've done a little bit of that so far, and I'll be able to show you that in this presentation as well. Next slide, please, Joanna. So we had to design an experiment, which is quite difficult in terms of a multi-fuel forecourt. So we had to work on the experimental design, and we also had to work with other Work Package 3 collaborators to provide experimental evidence as to the effects of hazardous occurrences affecting hydrogen dispensers and other dispensers on a multi-fuel forecourt. So we came up as a consortia with a group of scenarios that could be foreseeable on a multi-fuel forecourt. And we're going to go through those for you now. Today, we're going to focus on two of those scenarios as we've got a limited amount of time. So the first scenario was a burst hose resulting from a drive away from a dispenser. So you've got the hose and nozzle attached to a car, which then drives off. The hose is totally removed, so the whole hose is gone. The breakaway fails to shut, which from some industry experience and from some accident scenarios, we've seen that this can happen. So that leaves hydrogen being released from the outlet pipe, And what we did is we did ignited tests to understand the extent of that fire away from the dispenser. We also carried out a burst hose / hose whip experiment. So the scenario of this is a vehicle drives away, leaving the hose. So they've taken the nozzle this time, but they've left the hose. And what we wanted to do is to find out if that breakaway fails to act again and the hose whips around, whether the hose whip was enough of an ignition source to ignite the hydrogen released, and whether that was a possible mechanism. We also looked at internal dispenser pipework leaks. These tests were undertaken to understand the effect of a pipework leak internally within the dispenser housing from a small pipework leak. We're talking a tiny pipework leak of 0.2 of a millimetre diameter, a 0.5 of a millimetre diameter hole. And I'd like to put some context on how small a 0.2 millimetre diameter hole is. That equates to 0.031 millimetres squared in area. And that's sort of equivalent to a weep on a fitting. So if we don't fully close those fittings or those fittings start to loosen, that's what we're looking at. This hole size has been suggested before in standards such as IEC 60079-10-1, but usually used for lower pressures. When we're talking about representative leak sizes, we're usually talking, as Christoph has stated earlier, around the 0.1 and 0.25 millimetre squared areas for hazardous classification at temperatures, pressures such as 700 bar. And that again can be found in BSEN 60079-10-1 2021. So in these tests, so we've got these internal leaks within the dispenser housing. Both dispersion and ignition tests were undertaken. And this was to determine whether the concentration of hydrogen that could be found within the dispenser housing and the effect of ignition of that hydrogen within the housing, the dispenser itself, and on the forecourt surroundings. So that's what we're going to start to show today. Next slide, please, Joanna. We also did tests on internal pipework leaks within the dispenser housing, but placed then an ignition source outside of that dispenser housing. A strong ignition source was used in these experiments, and I've got videos of that to come. And the final experiment we did, because we needed to figure out, okay, if this is a multi-fuel forecourt, a traditional fuel, a hydrocarbon fuel fire could occur, and then in close proximity to the dispenser, and whether that would cause a leak path on the hydrogen system and become a domino effect for the dispenser. Next slide, please, Joanna. So today we're only going to talk about 2 of those tests, as we only got 20 minutes today. So we're going to talk about those internal dispenser pipework leaks with a size of 0.2 millimetre diameter. Looking at both unignited tests, so those dispersion tests that I spoke about, how much hydrogen can we get through a 0.2 millimetre hole into a dispenser housing with ventilation? What happens when we ignite those both externally to the dispenser and internally to the dispenser? And I'll be able to show you that to you today. Next slide, please, Joanna. So the experimental design, I needed to identify the points for an experimental design. In work package 3, key scenarios were identified for potential fire and explosion hazards. These included loss of containment on hoses, loss of containment externally to the dispenser, and loss of containment within the dispenser, all leading to a domino effect between different dispensers, both traditional and hydrogen. So we reviewed as a group the standards planning methodology work undertaken by Hydrogen Europe in work package 1. We also had conversations with stakeholders and HRS operators regarding forecourt configurations and dispenser design and housings. the outcome of studying the above sources that we identified there were two major evidence gaps that needed plugging with this experimental work. And that was separation distances, which is defined as the minimum distance allowed between hazards, and multi-fuel escalation. So what happens if we get a hazardous occurrence on one fuel? Does this then escalate to another fuel? Especially when we're thinking about a multi-fuel future, we need forecourts with several fuel sources on them. Next slide, please, Joanna. So how do we go about this? How did we make this experiment reality? A simplified mock dispenser was agreed with a consortium of height of 2 meters tall, 0.5 meter wide and 1 meter long. The housing was made with 1.25 millimeter thick 304 stainless steel, and the internal area of that is 1 meters cubed. There's ventilation holes at each side of the dispenser, and there are 2 openings, both top and bottom, on the lateral sides, each 120 millimeters by 100 millimeters. And these are representative of passive ventilation that is currently used. We needed to provide an experiment to estimate the effect of hazardous occurrences. So we needed to create those hazardous occurrences without impacting the safety of ourselves, the equipment of others on our site. So remote operation of the facility was enabled. And a hose was used to act as a potential breakpoint between the high pressure facility, the image on your left, and the dispenser and simulated forecourt, which is the image on your right. Next slide, please, Joanna. Brilliant. So some results. What we've done is on this slide is I've showed you one of the hydrogen concentration traces that we've got for one of the experiments. So this release size was a 0.2 millimeter release with that standard ventilation. So there's 4 holes in the side of the dispenser. It was a 700 bar release, and we did a 6-second release, timed release from the facilities. All the traces ran until natural ventilation reduced hydrogen concentration to 0. And what we can see here is we got a concentration of 26% was recorded within the dispenser. Measurements were taken at 5 locations within the dispenser, and it was found that the release above the release of point of hydrogen within the dispenser was the highest concentration. And we found that 2/3 of the dispenser housing was filled with 26% of hydrogen, but at the very lowest level within the dispenser, this concentration was lower. So if we remember that the stoichiometric point for hydrogen is 29.5%, this 26% is close to the worst case scenario for hydrogen. It's the most efficient concentration of hydrogen when ignited to produce the most efficient pressure generation, or as all of the fuel can be consumed. So this tiny hole, this tiny leak that we talked about, the weep on a fitting, has produced a hydrogen air concentration of 26% within the dispenser. Next slide, please, Joanna. So this is the first video of today's presentation. We have a leak within the dispenser housing from the pipework at 700 bar with a 0.2 millimeter diameter hole. We've used a strong pyrotechnic ignition source, which was stationed outside of the dispenser. If Joanna, could you press go on that video, please? So what you can see now is you see that strong pyrotechnic ignition source, hydrogen's being released. You then see that hydrogen being ignited and burning back into the dispenser. We can see the flames there, so we know that the hydrogen within that dispenser still being released, still ignited. And we can see here that the temperature generated from that, even after the ignition source has gone and the release is still ongoing, we can see that 2/3 effect. So we can see 2/3 of that dispenser housing is currently very hot. There's a fire in there, it's burnt back to the release, and that's continuing to persist. So that fire will go on for as long as there is a hydrogen source there. What we can see as well is that bottom third of the dispenser, which is where a lot of the equipment for this mock-up dispenser is there, isn't seeing the same heat. So we're only getting an upward propagating flame, which we expect for hydrogen, but we do have a jet flame there. Can we do the next slide, please, Joanna? Brilliant, if you click the first photo. So this is the point of ignition and this external ignition of that internal leak. So we can see we've got the hydrogen flowing out of the passive ventilation in the dispenser. We see that's ignited. We can also see that front door of the dispenser has been slightly displaced. So we can see that the inside the dispenser there is on fire. We can see there's some pressure generated, but it's not enough to cause problems to the dispenser housing. Next click, please, Joanna. But what did it look like inside when I was done? So we can see at the bottom there, facing upwards, is the release point. Above that is an aluminium housing, usually could contain hydrogen sensors, would contain pieces of equipment. That's all burnt out because the hydrogen ignition burned back to the release and a jet fire from there persisted. That actually sprayed the aluminium all over the top of the dispenser as well. And slightly above it, and if you click the next picture, Joanna, was a electronics cabinet. That was actually a powder coated intumescent cabinet. And you see that's been blown open with heat. You can see the intumescent coating has started to form its char, that started to burn away as well. So anything within that electronics cabinet, that's all been on fire, that's gone. Has my sound come back? There we go. And looking towards the dispenser, we can see that the roof of the dispenser has remained intact, but we do know that all the payment points and electronics within that dispenser will have been burned in this process. Next slide, please, Joanna. So this is a second test that we undertook. It's a small pipework leak, 0.2 millimetre diameter hole again, and that's occurring on the dispenser pipework within the dispenser housing. We'd already undertaken non-ignited tests to establish the concentration of hydrogen within the dispenser housing. So we know that's around 26% in this case. And then we did ignited tests to investigate the effects of ignition within the dispenser. This test was a 6-second release of hydrogen with ignition, along with another 60-second release of hydrogen. Could you press go on that presentation, please, Joanna? So this is in high speed, this is 1,000 frames. And what we're going to see is the internal ignition of the hydrogen. There we go. So what we've seen there is an internal ignition of the hydrogen at that 26%. And what have we seen? Well, we've seen the door rapidly ejected from the dispenser housing, impacting the side of the van, which is there as refueling. You can also see the dispenser housings rocking backwards and forwards on its mountings. Now, this is on very strong mountings, which is something we will look to for work package 3. We've seen the rest of the dispenser housings distorted and what's happened to the lid there. So that's what happens with an internal ignition with no mitigation in that system. Could we go next slide, please, Joanna? So what does this look like when we look at it in our IR mode? Could you press go, please, Joanna? Okay, so that's real time. So we can see how quick this event happens. There's no chance of escaping that situation. The doors hit the side of the van. And this is where we can really see with that persistent release what's going on and what's happening. So we can see yet again, we've got a sustained fire, which is being burnt back to the release and continues to burn through a dispenser. We can see that damage to the dispenser. We can see that the lid has been partially blown away from the dispenser. We see flames coming through that. We can also see flames coming out from the front of the dispenser. But the fire hazard is located primarily around that dispenser and hasn't then protruded further out. We see that the heating effect to the van is relatively minor. We're not really seeing that van heat up at this point. Next slide, please, Joanna. So a few more photos as to what happened. So what were the effects? The impact to the van, which was of sufficient force to wrap the reinforcement and warp the reinforcement in the van to the side of the wheel arch. So we can see that's all distorted. If this were a car, the windows in the back door would have shattered with the impact force. The impact effects were also seen on the dispenser door, which when removed remained in the impacted shape. So that shape that you see in the van and in that dispenser door, that remained the case. Next slide, please, Joanna. So what happened to the rest of the dispenser? Well, we can see that there's several points where the dispenser has bowed and popped. Housings popped away from the skid, and that was connected at 6 points down the back of each panel. So it was really well attached. We could also see that the lid on top of the dispenser, which we had used for increasing ventilation, has also popped away from its fixings. There were 6 of those, but hadn't fully removed. I think this is partially due to the vent line in the top, that didn't occur, and also that front door provided all the pressure relief needed for that to remain partially attached. But it was a large amount of pressure generation in that system. Next slide, please, Jana. So the pressure wave exerted on the forecourt was not sufficient to cause primary blast injuries. However, secondary blast effect, i.e. impact from the dispenser door or a structural forecourt item which has been impacted by the piece of the dispenser housing, would be sufficient to cause serious harm / fatality. The ejection of the dispenser door occurred with overpressures of 620 millibar. The distance between the van and the dispenser was 0.8 of a metre. So the design of a dispenser housing will inform the potential for pieces to be ejected from the housing following an internal ignition event. The orientation of a weak point, such as a door, should be considered, and a potential barrier / tethering between the weak point and the forecourt to reduce the velocity of an ejector panel could also be considered. So this is moving more towards what could come in work package 3. And we saw that localised fire, which extended from the dispenser to the van stationed until the release ceased. Next slide, please, Joanna. So we started to talk with Christoph about what mitigations could be used to prevent the most hazardous consequences on a forecourt. So we installed a foil blowout panel that was installed at the top of the dispenser, replacing the original steel lid. We did the scenario again and to determine whether this was adequate mitigation of the scenario. And this the video that's got the noise on. So if you're prepared to reduce your noise levels on your own control, Joanna, if you want to press go. And if we stop there, Joanna. Thank you. So what did we see there? So we saw that top foil panel blow out as we expected it to do to provide that mitigation. We saw that the door distorts with the pressure that's generated from an internal ignition, but the door wasn't removed. So that inclusion of a foil panel did prevent ejection of the door. It does give a bit more possibility of escape, and it's preventing some of those secondary blast effects to occur. The dispenser also remains on its mount. We haven't got a rocking dispenser this time. We've got a more controlled situation. So there will be levels of mitigation that can be included in dispenser design, and I know this has been looked at in work package 3, that will greatly improve the situation. Next slide, please, Joanna. So what we saw, an inclusion of foil panel as part of the dispenser, housing to act as a pressure relief or blowout panel, did improve the situation. We found that it partially relieved all the overpressure generated. However, it did not prevent the bowing of the dispenser door or the jet fire which ensued inside the dispenser. So we still got that jet fire, we still got big damage inside the dispenser housing. The blowout panel could prevent the majority of secondary blast effects on persons, depending on its orientation on the panel on the forecourt. And that's something we really need to be mindful of. However, the placement of that mitigation measure should be considered as part of the overall forecourt design, as it could introduce different hazards. Next slide, please, Jana. So we spoke about, and Sebastian presented earlier, the different configurations. So this is configuration 1, a ready to deploy multi-fuel station. And the green circles there are individual canopies as shown. So if we think about how this may affect the results that we've seen, may affect the deployment of a multi-fuel station. On the right of this picture, you can see there are multiple dispensers in a line in between the cars. And obviously, if you're getting a blowout of a dispenser such as that, there is potential then for that to escalate to other dispenser types and potentially increase the likelihood of a domino effect. If there was not a vehicle stationed at the dispenser acting as a barrier, that ejected piece of the dispenser could travel outside of the forecourt or towards different technical and control rooms as well. Next slide, please.
So as you saw, these are our direct experimental results that we got from the project activities. And with that in mind, without further ado, because we're a bit late with the schedule, I'm going to give the floor to David, who will present hazardous area classification examples, which is the follow-up of the consequence analysis that we just showed from Luis's video. So David, hope you're here with us.
Hello, hi, can you hear me?
Yes, we can. Please,
Excellent.
the floor is yours.
Thank you very much, Excellent. So next slide, please. So what I am going to present is part of the work that we did as part of Work Package 3.6 that was basically using the good practices, the standards, but in addition, relevant experimental data for Work Package 2 in order to create examples of hazardous area classification, and we divided this into internals of the dispenser, what will be the zone inside the dispenser for a specific type of release, and external zones was the second part, what will be the zone around the dispenser in because leaks or because of a vent scenario. Before doing that, we did a benchmarking and we reviewed different points, definitions, hole sizes, methodologies for zones of the vent, and the main aim of this was to gather a lot of information of the whole size, use it for different applications. So all of this is part of one of our deliverables. And what we found was that there are several whole sizes used in the industry, most of them based on 2 or 3 specific values, but there is still some harmonization to be done, and some of that doesn't necessarily apply or were based on hydrogen technologies. So if you can move to the next slide, Dinko, please. So this is the standard suggested values. That depends on the operation, and they are depending as well of the type of parts. So that goes from 0.025 millimeters square up to, depending of the operation, 0.25 millimeters squares, or even bigger if there are other parameters. So then there are other, if you go to the next slide, um, other sources or in the literature in which hazardous area classification have been performed as well. And for example, for the addendum of the Blue Book on the left side, and as well for BCGA GM13, there has been some indications, and the distance is calculated based off 0.1 millimeter hole size, which is smaller than other references. So what we did was we took several of these values, and we tried to do a hazardous area classification example. Um, uh, Using the different hole sizes that we found, and in order to give a sensitivity and to show what would be the effect. So what we did was we followed the main requirements of the international standard IEC 6079-10-1. We did follow the annexes in order to determine the zones, the degree of dilutions, but as well, when we're external releases, we use quad vent and fast, and we determined the zone and the extent. And the aim of this project is not to suggest a specific hole sizes to be used, but rather show what will be the conclusion using the different hole sizes that have been found in the literature, and give some guidance of what are the parameters that needs to be considered in order to select this. But it is up to each designer to decide which is the most appropriate hole sizes that will define their technology. What is the main case? We took a simplified um, volume, very simple. We assume a rectangular one with minimum elements inside, and we determine the internal zone if there is natural ventilation. If we assume that forced ventilation is possible, what will be the requirements in order to move the zone? And then we determine external zones, especially from leak points on around the hose, around the receptacle, and well, the nozzle. And as well, we analyze it venting the system. So I will mainly discuss here, because of time, the internal releases. So if you can go next slide, please. So, well, internal releases. So what we did was try to determine internally what will be the degree of dilution. For that, we estimated the ventilation, natural ventilation we expect to have, and as well what will be the release rate inside in order to determine the zone. We use the rated pressures that are in service, 70 megapascal, 35 megapascal, and we did the calculation for the maximum operating pressure and the nominal pressure on each of them. We follow 2 main requirements of the standard. One is figure C1 to determine the degree of dilution, but as well, in order for avoid as well a degree of dilution that is not low, needs to be the concentration, background concentration needs to be below 25% of the lower flammability limit. And next slide, please. The first estimation was to determine what is the natural ventilation within the system. So what we did was we assumed two different. This was made as well before of this work in another section of work package two in order to determine what was the velocity of air if there are wind velocities of 1.5 meters per second or 5 meters per second at 10 meters. That is the standard height that these are measured, and then corrected to the height of the vent. And we were assuming two different rural and city. The standard does have some equations to determine the ventilation velocity. As I mentioned, as part of this project, there were as well estimations that can be done using Quadrant, if we reach the same conclusions or based on the same assumptions and equations. So we determined what was the ventilation. Next slide. At the, can you help me with the next slide, please? Thank you. So as I was mentioning, there are two nominal pressures that we analyzed. I am presenting here the extremes, even if they are not related to the same. So the maximum operating pressure for hydrogen operating a 70 megapascal, and what would be the nominal pressure for one dispenser operating at 35 megapascal. And basically what we found is using the figure of the standard for different leak sizes, we estimated what will be the release characteristic, and what and with the ventilation's velocity, what we determine, some of them will be within the consideration of medium dilution, especially for the lowest pressure. However, when we check this with the condition of being below 1%, so 25% of LEL, or background concentration, assuming a really good mixing, which is already another assumption, only one of them will be within. So most of them will depend on the ventilation velocity, and is, well, very variable. So the conclusion is basically the low dilution will be characteristic of these kind of installations. So which will mean that in case of a secondary release, low dilution with the ventilation openings that we assume it for natural ventilation, the most likely result is that it is at least someone within the enclosure. And some experimental results of and also very close to 0.025 millimeters squared, that is around 0.2 millimeters, just above that. We can see that it reaches considerable concentration, so it does support the idea that this kind of release without any control, abnormal atmosphere will be present for long duration of times. So it does support the results, does support the assessment. If we move to next slide, please. In order, basically what this is mentioned is in order to be able to have a lower zone, so for example, zone 2, additional ventilation will be required. So if we calculate this, by calculating, assuming a perfect mixing within the enclosure, will mean that we need considerable ventilations. So at lower pressures, these well are values that are considerable, well, that are possible. But if the installation are could have considerable hole sizes for hazardous air classification, like 0.1 or 0.25 millimeters square, the ventilation rate will be very big. And even for some dispensers already being able to provide any means of additional ventilation could not be practical. And if the hole size are considerable, it's just not possible. So someone maybe at least someone maybe the final result anyway. Next slide, please. However, what we wanted to review is a lot of the current protocols, or let's say requirements for hydrogen refueling stations. They require what it is called a pressure hole test, or pressure integrity test, from the dispenser up to the vehicle. that even some of these requirements, or I think NFP to require, depending of the difference of pressure or how much hydrogen is being filled, to test. So this integrity test basically is a pressure leak test continuously or very recurrent every time the a vehicle is going to be refueled. So we wanted to analyze if this will have a potential way to detect leaks that are around the whole sizes usually used for hazardous area classification. And next slide, please. So when we review well, the work performed by the Health and Safety Executive in the work, this is a release that is a 60 seconds release for a nozzle of 0.2 millimeter, as I said, very close to the 0.025 millimeter square. We can see very quickly that if the release is done and the high pressure storage is connected to the release to the nozzle, there will be, well, minimum decrease of pressure within the volume of the dispenser, of the pipe of the dispenser. But as soon as the system is isolated, the pressure will decrease very quickly. So that is basically if there were to happen a pressure integrity test with this type of hole sizes. That's what would potentially happen in a limited volume, and uh, a lot of the tests being done within a dispenser from an isolation valve inside up to the vehicle will be recurrent pressure decay tests. Will probably be a good idea in order to support or to at least continuously check that there are no leaks. It's still limited. It's still well a release given the pressure working. However, parts that are still within the dispenser that are not subjected to the pressure integrity test, let's say upstream data isolation valve, well, they potentially could present bigger leaks because they are not tested, that they could have bigger leaks. So this is something to be considered and reviewed if there are possibilities to everything within the enclosure to be continuously tested like that. So yeah, that would be the part of internal releases. For external releases, what we did was to review different methodologies. If you go to the next slide, please. Basically, the different methodologies and different hole sizes, and try to review the differences and understand very well why there were differences in the results. So if you can as well go to the next slide. I'm not going into the detail here, but basically we use FAST as one of them with different atmospheric conditions, so different wind velocities and different atmospheric stability factors. Well, that will have an impact on the result. And therefore, then what we did was compare with Quadben and the annex. And if you can go to the next slide, we did for different hole sizes and presented only two. Again, we are not suggesting of a specific point, but the main thing that I wanted to show here is the annexes of the standard. Quadben doesn't consider any contribution of wind. Is basically a stable or very low velocity conditions. So there are considerable effects when the wind velocity is considered as fast, or any other software that could provide that. There are jet and diffusive correlation in the standards, which the jet correlates quite well with the distances for Quadben. And other factor we analyze here is the effect of temperature, and that's what we suggest as well to review very well. Lower temperature of the gases increase the release rate, and higher temperature of the ambient wall as well limit the dilution externally. So choosing those parameters are quite important for the result in order to provide a good description of what we actually are expecting to have. So yeah, those kind of conclusions. Next slide, please. We reviewed as part of the work as well if we, for some reason, well, not for some reason, after given after a refilling of the vehicle, if there is the pressurization of the system up to an isolation valve, well, how will be the zone around the vent if there is a specific restriction orifice, or what will be the worst case scenario if there was no restriction orifice inside. So what we as well wanted to look at is what will be the conditions of the zone for different type of venting points, if you want, and we look at this type of example. So what we did was to again review different atmospheric conditions and the effect of a specific restriction orifice that will limit the leak within the, well, not limit the release or rate during the dispersion. And therefore we did the same for using different models. However, a lot of these assumptions are basically, we can go to the next slide, please. Were based on the fact that we basically calculated what is the release rate that we will have a specific pressure for the conditions of, let's say, a restriction orifice limiting and the additional pipework. What in reality happened in these conditions are there is a limited volume that where this will be basically the worst case scenario, and there is not enough volume to maintain the release rate that we're calculating. Therefore, all of these are conservative, but what we can find is basically that when the restriction orifice at this pressure is quite more than 1 millimeter, basically the extent of the figures of the annex of the standard, well, are outside, so are outside the range and are suggested not to be used. And then for quad ventile, it's a simplified model, not necessarily developed, in my understanding, for this kind of venting releases, but we will have considerable release rate. Then for softwares or tools to consider the effect of when there is a reduction. When the restriction orifice is there and we can't use the annexes, the releases or the what is considered obtained by the standard is not is of the same order of magnitude of fast. And basically that's the when we consider fast, we have done some calculations if we have a constant release, but as well the effect of considering only the limited volume. So we did this mainly for a horizontal release, and we do suggest to having to account this factor, as otherwise there could be overestimations of the zone around the vent, and the limited volume will have an effect in which we found that for the worst case conditions it will to reach a 50% LFL zone horizontally. For this case will be 7.5 meters. If it is assuming only pressure and the flow rate through it, it could go to 12, 30 meters. So it's quite conservative. And I would like to finish with some conclusions here. If next slide, please. For the cases that we analyzed it in this example, at least a zone 1 where natural ventilation was determined, additional ventilation will be required, and for each application it is required or to do an assessment of ventilation and release rate, because several variables, there are a lot of variables that will have an effect of the on the result. Non-hazardous zone classification is in the dispenser is not possible, at least for the work we have been looking at, and any addition reduction of zone will require high flow rates. The small hole sizes assumption is to be used with caution and is to be very well understood why. Pressure integrity checks in the dispenser are performed regularly and could be implemented in several parts to improve the leak rate or the reduction of the leak rate. External source should consider a safety factor to the lower flammability limit. I will come back to some of these assumptions. conclusions. And the zone will be very dependent of the hole size externally, but as well of the type of software, depending of the assumptions that are behind it. So Quadrant does have the ideal gas assumption does have an effect, and there are some of the software that could have the effect of wind that will have an effect as well on the extent of the release. With that, I will stop here and give the word to my colleagues.
Yes, thanks, David, for such a quick overview of this extensive example. With that in mind, we go to the next section with the recommendations that we developed, which are the main part of this deliverable. And with that, I will give the floor to Nick from ITM as well to go through a couple of recommendations that we would suggest. Of course, the extensive and the detailed information you can find in the deliverable that will be online, uploaded afterwards, but we try to summarize as much information as we could in this short time. So, Nick, the floor is yours.
Thank you. Thanks, Tinko. Okay, so just to give a sort of trajectory for where we intend to take the recommendations that have come from the project. But you may or may not be familiar with it, but ISO TC197 is the main ISO standards committee for development of standards and other technical guidance for hydrogen technologies. There's a bit of information there if people want to look into that. But the three most applicable documents that we believe the output from the product is useful for consideration within is the ISO 19880-1 for gaseous hydrogen fueling stations. That covers the general requirements. ISO 19880-2, which was recently published for dispensers and gaseous hydrogen fueling stations. Then also ISO TR 15916, which covers the basic considerations of safety of hydrogen systems. If we could just go to the next page, thanks. So there's two of these documents are under revision at the moment. That's the 19880-1, which is anticipated to be revised the near future. And also TS 15916 is undergoing a technical specification. In working group 29 of TC197. And then additionally, what might be worth consideration is CEN-CENEC Joint TC6, which is a European committee covering hydrogen and energy systems, as working group 3, which is developing what hopefully will become a future technical specification for hydrogen systems in enclosed spaces. So as you saw from a lot of the work that has been presented within the dispenser, then this is a prime example of an enclosed hydrogen system. And then finally, as David's been talking about, the explosive atmosphere side of things is covered by IEC TC 31 within SC 31J in IEC 60079-10-1, which is under revision as well at the moment. So we're trying to contribute to the development of that, either the next version or a future version after that. Okay, thank you. So if we can go to the next slide, then this is just a summary of the recommendations for the dispenser that were included in the deliverable that we shared soon. And as you saw from Louise's videos, then you saw how critical it is to include within the dispenser design openings or apertures, both for natural ventilation and explosion panels, which we'll come to in a minute. But certainly openings and apertures for natural ventilation and wind reinforced ventilation are essential to reduce the potential for accumulation in the case of a loss of containment, particularly a smaller loss of containment. And then one of the recommendations from the project is that horizontal ventilation apertures, particularly in the upper areas of the dispenser, are more efficient or more effective to enable wind to provide ventilation, in whichever orientation the wind is coming towards the dispenser. Maybe fairly obviously, but hydrogen detection within the dispenser and a associated emergency protocol or actuation of isolation valves in the case of a detection of hydrogen at a certain threshold. Explosion panels, there's a couple of slides that I'll come back to. And then things like early detection of releases from either distributing hoses, and the protocols require very short detection time and reaction times, which may even be the response time of those may be required in certain regulations for refueling stations. And then another recommendation is to consider the installation of restrictive orifices or excess flow valves in the pipework upstream of the dispenser to limit the flow to the dispenser in the case of a catastrophic failure. Obviously, though, that needs to take into consideration the requirements to enable sufficient flow rate to go to the dispenser for the fueling of a vehicle. Okay, next slide, please. Fairly typical in dispensers now, but if not required, but the use of a breakaway coupling to isolate the system and limit the hydrogen inventory that's released in the case of a drive-away event. Also, an isolation valve within the dispenser that the control system can then isolate the hydrogen system from the dispenser and limit the inventory release in the case of a significant loss of containment or failure of the breakaway. David's talked about the hazardous area classification. Obviously, that's important to make sure that electrical equipment and other potential ignition sources are suitable for the zone in which they're installed, and then ensuring that grounding of the equipment in the dispenser, including the dispenser nozzle as well, is achieved. Okay, if we go to the next slide. So these are some of the recommendations for explosion panels within the dispenser, which Louise's videos show how critical they are. And the second dispenser where we saw that have minimal effect from the same explosion. So there are recognised standards for explosion panels, and for the 1 meter cube dispenser housing that was used in the experiments, then the vent areas are quite significant at 0.9, 1.2 meters squared respectively. They give you a guidance of a methodology for determining the size of the panel, but it's recognised that sometimes this can provide a conservative result on the required vent area, and there may be empirical models that can be used to demonstrate smaller vent areas that lead to the same reduction in overpressure. But obviously, if you're using standards or other models, then you need to perform careful checks to make sure that you're not compromising on safety. So in our case, in the experimental setup that was performed in the MultHyFuel project, the dimensions of the dispenser, 2 meter high with a relatively thin 0.5 meter width. It had a aluminium panel, I think, of about half a square meter located on the top, which was essentially equivalent to the entire footprint of the dispenser. And it's below what's required in the relevant standards, but obviously there was a little bit of extra venting through natural ventilation apertures and the open bottom of the dispenser. There was a small amount of plastic deformation in the, as we saw, the door, the opening to the dispenser was deformed slightly. The standards do specify that a vent area should be adequate to prevent plastic deformation. And designers obviously should consider whether or not the damage to the dispenser is acceptable, but at the same time ensuring that there aren't fragments or things that can cause harm to people in the vicinity. So next slide, please. Thank you. Yeah, so if people don't use the standards, the two standards that we've suggested are examples of standards that can be used for sizing explosion panels, and there should be some reliable modelling or thing to demonstrate their efficiency and suitability. One of the points that we want to we would recommend is that whilst it's ideal for dispensers to be as short as possible, the location of the explosion panel should be above head height, at least 2 meters in height, to ideally orientate the explosion relief in an upwards direction, so it's not going to hinge on someone who's stood nearby. Yeah, and from the testing that we did, the vent size was approximately adequate for the size of dispenser we tested. One of the things obviously is requires thinking about as well is when you're integrating a dispenser into a forecourt, then you need to take into consideration other things in the vicinity of the dispenser that could impact on the efficiency of the explosion vent panel. So any obstructions that could reduce the effectiveness of those, for instance, walls or a canopy on top of that. Okay, if we go to the next slide, please. Just a final recommendation for canopy design. So that's obviously less applicable to the dispenser itself because it's about the way that the dispenser is installed into a refueling station. And I will note that canopy design wasn't a significant part of the MultHyFuel project. It's just an observation made following the project. That canopies obviously should be designed in a way that avoid the accumulation of hydrogen releases, whether that's from inclining the roof at an angle or having sufficient distance between the dispenser roof and the canopy to prevent buildup, or an alternative, well, not an alternative, but one mitigation that could also be considered is have an individual canopy over a dispenser where that's applicable, so that if you have a collapse as a result of ignition, that the harm is the risk to people is in a very localized environment. Okay, so I'll hand over to David now for some recommendations on hazardous area classification.
Thank you very much. Well, I will go quite quickly because we have discussed the hazardous area classification methodologies define descent to releases to a lower granularity limit due to uncertainties on the dispersion and ignition. Mainly, modeling gives average values, concentration over time, and not necessarily take the instantaneous concentration of gas. It is recommended to designers to consider the application of a safety factor to a lower granularity limit. The local conditions of wind, temperature, as I mentioned, is to be taken into consideration as they may have an effect on the release rate and dispersion. We reached the conclusion that whole site selection for hydrogen technologies requires further research and analysis, and this is something that is being discussed on different groups as the values that are suggested in different literature or rough guidance are not well understood and not necessarily, or the derivation doesn't necessarily apply to some hydrogen technologies. Small hole sizes, as I mentioned, is to be justified and used by caution, and it is recommended that at a very minimum pressure integrity checks are used within the dispenser and performed regularly. Within, well, this is a standard, but within any hazardous zone, operators shall ensure control of ignition sources as per regulations and apply restrictions or procedural controls in order to make sure that unexpected ignition sensors are not brought to the zones. And for each application and assessment of ventilation and release rate will need to be performed. The example that I presented had different assumptions, and it will be different depending of the design and the installation in general. Next slide, please. To finish, I think on external relations, as I mentioned, on venting, it is recommended to evaluate what is the restricted volume of what are the release rate, as well provided by the consideration of our restriction orifice. So on the estimation, as I mentioned last time, this is basically the same conclusion, is for releases around the dispenser needs to consider the hole sizes, and as well the dispersion tool needs, there are several assumptions behind. if a justification for small hole sizes are not possible and bigger hole sizes are required, well, the STEM will increase considerable. For example, 0.1 millimeter square will provide 4 meters using pass or 6.5 using quad, and so it is quite critical to make sure that the right hole sizes describes the installation, and the small hole sizes needs to be used with caution and justified very well. Yeah, I will give the word to my next colleague. Thank you very much.
Yes, thank you, Nick and David. We'll move on. As David mentioned, we need further analysis. And we have technical suggestions for further research, which will be covered by Sylvain again. And without, of course, further ado, I'll give the floor back to her to cover shortly what are the technical suggestions for further research and harmonization of good practices. And are you here with us?
Yeah.
Yeah, we hear you well.
Yeah. So I represent technical suggestions for further research and harmonization of good practice. So next slide. So the prenormative research carried out with the confines of MultHyFuel project lead to the identification of some gaps in knowledge that may need to be filled in order to inform codes and standards. There also remain some separate general knowledge gaps which were excluded from the projects, so which needs to consideration and investigations, some of which are already in progress by other projects that you see just after. So, for example, indoor high response, high responder, Presley shift. Next slide, please. So, as mentioned by Julian, there is no data in MultHyFuel provide for the liquid hydrogen release. So we have to see also other projects such as Presley, Shift, or May I Save, Alvis. Next slide, please. So the dispenser design, it's important that the current work is based on the dispenser designs developed in the following norms. For new dispenser design specific considerations, a dedicated assessment should be carried out by the designer. Also, for specific atypical design of dispenser, the design of venting explosion panel should be investigated further on a case-by-case basis. And also for specific atypical design of dispenser, the impact of internal obstruction level in the upper segment of the dispenser may be investigated in terms of the severity of the explosion in case of the ignitions. Next slide, please. So the safety of the fourth quote, in the risk assessment of the installation, we should consider detailed information from supplier of breakaway, for example, the failure rates and modes, and also analyze potential human factor to ensure risk is kept as low as reasonably practical. In addition, there need to be further research in the emergency shutdown system on multi-fuel forecourts. For instance, combinations of detection system and shut-off valve actioning should be investigated with initiation of a release of hydrogen, taking into account the response time of the systems. Next slide, please. So about the modeling approach, further investigations into existing modeling approach may be requiring additional experimental data, address the assumption and limitation of the existing simple analytical models, and provide recommendations where numerical simulations brings added value to inform risk assessment methodology and assumptions. We have also to carry out more detailed investigations, experimental, but also numerical modeling into complex scenarios. For example, when there is domino effects between different fuels other than hydrogens, taking into account realistic characteristics of multi-fuel stations. Next slide, please. About the interaction between hydrogen and other fuels, we have also to have investigation for the interaction between hydrogens and the other conventional fuels like gasoline with a single dispenser compressor units should be carried out. The integration of hydrogens with us on the same dispenser as the other conventional fuel and necessary to prevent or mitigate barriers, taking into account the potential domino effect, including a flammable acceleration mechanism and resistor houses, all types of fuelings. Next slide, please. Further attentions, the work conducted in this project has identified several specific areas that would benefit from further attention and exploration by relevant regulatory records and standards, bodies and organizations. Good practice could be represented via an example multi-fuel hydrogen refueling stations model with design layout recommendations and minimize fire and explosion risk in compliance with national regulations to protect people. For example, we can have reduction of leak points to prioritize the control, so prioritizing preventions, over mitigations or engineering control over mitigations, promoting installations that are highly ventilating to prevent hydrogen accumulation and confinement, and inspection of installations. Next slide, please. About suggestion for engagement between national regulator and relevant stakeholder. It's for us necessary to have harmonization of scenario and criteria, threshold and liquid size for the definitions of city distance for multi-fuel refueling stations, to review procedural control measure to maintain exposure to member of the public to a minimum in line with standard and guidance, and also the lower explosive limits could serve as a complementary or even primary basis for defined hazardous zones. It can be used also to reference for hazard distance, aligned with a preventive safety philosophy, and may address a situation where an ignition source could be present outside the visible flame envelope. Its approach could offer an additional layer of conservative and robustness to risk assessment. Next slide, please. So about experimental research, modeling and hazardous classifications, the expanded validations of leakage rates for forces source through experimental data and experiment operational experience. It's necessary also to review hazardous area classification methodology approach to consider the specific characteristic of hydrogen technology, including realistic release scenarios for all size, for example, and the dispersion characteristics. Next slide. About the likelihood, we see that there is, we propose a new methodology, but we need to validate this new methodology with more data. We review also for the initiation probability. We have also to review the variables affecting these initiations, the probability of initiation to inform the risk assessment. Next slide, please. About safety barriers, it's important to develop inherent safe design for multi-fuel dispenser to test the effectiveness of various safety barriers to answer satisfactory mitigations response. For example, the detections to response time to full stop leak chain, including detection and require action to stop the leakage. It has to be considered to determine the confidence level of seal requirements for safety barrier to reduce the probability of hazardous scenarios. About safety barrier, it's important also to explore additional procedure control and maintenance to prevent or reduce potential static accumulations, for example, to the involvement of members of the public in the refueling operations. It's important also to develop ultra-rapid hazard detections that can react and isolate the system in a couple of seconds, for example, acoustic detections. About also safety barriers, assaying the use of fire and blast wall as mitigation for the station's backyard, so the technical area. It's have to be also understand from the station designer that when we install some fire or blast wall, we have to avoid to counter mitigation effects. For example, the increase of to put a wall can increase the degree of confinement of a potential blast and leading to higher overpressure. About also inherent safe designs, it's important to explore the feasibility of a single dispenser capable of handling all fuel type, including hydrogens, to, as said Nick, investigate different canopy design for multi-fuel hydrogen refueling station facilities, and also to adhere to the principle of inherent safety for the design of the hydrogen refueling station and forecourts. For example, to minimize inventory in the backyard, to minimize operator-based task, and eliminate the opportunity of error. About material compatibility and maintenance, it's important to examine material compatibility and potential defects due to the hydrogen's compartments, also to enhancing cleaning procedure for hydrogen systems, and defines some maintenance regimes, including periodic leak test and inspection procedure. About organizational measure and training, it's important to establish good practice and organizational management and to train all the operators that are around the stations. Operator, but also competence management, but also every person who make the maintenance and assembly of hydrogen refueling stations. Next slide, please. About the risk considerations in the backyard for multi-fuel stations, it's important to have a detailed study of risk associated with all the equipment, the storage, permanent storage, as temporary storage trailer, for example, compressor and process equipment for the different fuel, including conventional and considering the potential domino effect. It must be also careful considering the setting of multi-fuel refueling station of paramount of the importance. Next slide. So to conclude, these considerations emphasize the importance of throughput, multidisciplinary efforts to advance the safety, reliability, and efficiency of multi-hydrogen refueling stations, and to be ensuring they meet both current and future demands. It's finished for me.
Thank you, Solène. Thank you to all the colleagues. You see that we have a lot of information within these deliverables. We try to summarize them as much as we could. What I suggest once more, try to check it online. We will try to upload it during next week, so you will have access to it. I just want to really quickly close the project activities, actually the post-project activities that we're working on. We have the website, which will be up and running with the deliverables and recordings of these events, including this latest event. What we suggest, since we didn't have time for the Q&A, what we would suggest, we have 2 contact emails where you can send until July 31st all the questions that you have related to the documents that we will upload, specifically the deliverable 347, which we're focusing on today. We will aggregate those questions, send them to relevant partners, and try to provide to all participants the responses to these questions, to having relevant information, the feedback that you. One other thing that we need from you, that we would ask from you as stakeholder, is the letter of endorsement until July 17th. What this is about, this is not such an obligatory letter. This is just information that you have acknowledged, understood the outputs of our project, and when you'll be working on either implementation of your refueling station as a public authority or HRS operator, that you will take into consideration the outputs of our project during the implementation itself. We would ask you to provide us this so that we know that we have contributed quite significantly with the project outputs, with the results that we got. As Nick and all the other partners mentioned, we are quite closely working with the standardization groups, trying to assist them with the results that we got. So this would be quite significant to us to have this. The recording of this event will be uploaded so you can hear it again. Thank you all for participating. Thank you to all the partners and people presenting for taking time working on this project. It is a pleasure to close this project, since it took quite some time for us to get there. Quite a lot of bottlenecks that we stumbled upon but managed. And with that in mind, I would thank you for your attention. Thank you for your participation and following us throughout these years. And looking forward and hoping to see you with the next project that we will have as a follow-up of MultHyFuel. And with that, I would wish you a nice rest of the day. Bye to everybody.